We will continue our discussion on IC engine. In fact, today I will continue our discussion with carburetor. We have discussed about the function of carburetor, that is to supply a homogeneous mixture of air fuel and also to supply air fuel mixture depending on the load of the engine. And we have seen that what is the stoichiometric air fuel ratio, or what is the rather chemically correct air fuel ratio. So, the function of carburetor is to provide the chemically correct air fuel ratio, but it is not always possible to supply chemically correct air fuel ratio, but we have seen for a given fuel there is a combustible range. So, carburetor will be able to supply the air fuel ratio or fuel air mixture within that range, and if the supplied air fuel mixture or fuel air mixture goes above or below that range, then combustion may not sustain. That is what we have discussed in detail in my last lecture. Today I will continue what is different parts of the carburetor, and as I said you that the carburetor, the function of carburetor is to provide chemically correct air fuel ratio or the air fuel ratio within the combustible range. Then in fact we have discussed maybe that when we are doing analysis either for auto, diesel and dual cycle, we are using the air standard cycles, and we are doing air standard analysis only to quantify the thermal efficiency. And we have seen that while we are doing air standard analysis, we are assuming that air tube and ideal gas, and also we are using ideal gas relationship. Now question is, we have discussed about the major differences from real processes occurring in an internal combustion engine, and the processes what we are considering using air standard analysis. That means we are assuming that the air tube and ideal gas may be in case of a SI engine, during inlet all may be air, maybe 7% of the fuel, but in other exhaust stroke or exit this is a combustion product. So, my question is, when you are supplying air plus fuel during intake stroke through carburetor for SI engine, most of the composition is air and very small fraction is fuel. So, when you are designed a carburetor to supply maybe 90 or 93% air and 7% fuel, then what are the structure, rather how a carburetor is supplying most of the air and small amount of fuel. And for that today we will discuss a simple float type carburetor, and we will see how it is possible to supply fuel air mixture through a carburetor depending upon the load, or also rather the chemically correct air fuel ratio. So, today I will discuss about a simple float type carburetor. Simple float type carburetor. Although these are not used nowadays, but still only to have an understanding about the processes which is there in a carburetor, how a carburetor is applying air fuel ratio or fuel air mixture depending upon the requirement of the engine load. We should discuss this in detail. So, simple float type carburetor, while you are designing, we need to draw the schematic. I mean what are the safe, rather what are the constructional feature of a simple float type carburetor. So, if I draw, as I know that air is coming through intake manifold, right. So, air is coming through intake manifold, right, and we are supplying I am drawing a simple float type carburetor. And we are having one float over here, and which is connected with this. So, from there we are supplying fuel from fuel tank. This is air vent, and this is the float. This is fuel tank, and if this section is AA, maybe this is section A, this is here we are having one throttle valve that is there. This is intake manifold, this is intake duct or manifold, and sometimes we measure a venturi, sometimes we connect venturi here, right. So, maybe this is the pressure drop. So, this is venturi only to measure the pressure drop that I will discuss, and we are having this is tip of the jet tip of the fuel. So, maybe this is tip of fuel jet, right, and this height may be delta H, and this section is BB, this is section BB, right. This is calibrated orifice, and this is calibrated orifice, this is throttle valve, right, and this is fuel, and this is fuel discharge tube, this is fuel discharge tube, right. So, and this is float chamber or fuel tank, this is float chamber, not fuel tank, fuel is from fuel tank, and this is called float chamber, right. This is the different parts of a simple float type carburetor. As I said you that air is coming from top. So, air is coming from top. So, this is incoming air. So, air is coming from the top through air duct through intake manifold. So, if I try to recall what is happening in a spark ignition engine, Direct intake stroke, piston is coming from top dead center to bottom dead center. While piston is coming from top dead center to bottom dead center, intake valve is open, exhaust valve is closed. We are creating a pressure difference between the atmospheric pressure and pressure inside the cylinder. Rather, we are creating a vacuum inside the cylinder, and that vacuum will create a pressure difference, rather create a driving force for the supply of air through intake manifold from ambience to the cylinder. Now, air will rush from ambience to the cylinder through intake manifold. Now, while air is coming, then we have to supply fuel at the middle of the intake duct, so that incoming air velocity will try to fragment the fuel particle in a finer droplet. But since if we do not have any pump, rather here we are having float chamber. So, because of the pressure difference between the cylinder and the ambience, air will come through intake manifold to the engine cylinder through intake duct, but we have to make an arrangement such that the pressure difference while air is coming from ambience to the intake through intake cylinder to the engine through intake duct to the engine cylinder, we can have also supply of fuel from float chamber to the that is the through fuel discharge tube at the in the intake duct. By how? So, there are two ways of supplying fuel. Either you have to have one fuel spam, so that I can spam the fuel from float chamber to the intake duct, or we can utilize again a pressure difference between the middle of the duct, rather where the fuel is discharging, rather tip of the fuel jet, and also the that is atmospheric pressure, because the float chamber is open to atmosphere. So, at the top of the fuel level atmospheric pressure is acting. So, if I now create a pressure difference between that these two section, maybe between the level of the between the atmospheric pressure that is there on the in the float chamber, and the pressure which is there when fuel is discharged, fuel is being discharged through fuel discharge tube. So, to do that, what we have to do? We have to do a necessary arrangement. How? So, we need to provide a that is very important step, that is known as by how we can provide, by how we can create that pressure difference. So, we will provide a projected areas must be provided. So, we can provide a projected area at the middle like this, rather we can provide a this projected area at the middle where fuel is discharged while air is coming. So, what will happen if we provide projected areas like this? That means when air is coming and when air is approaching this portion, the section BB, then we are doing a reducing the area. So, because of the reduction of area, flow velocity of the air will increase. Because of the increase of the flow velocity, pressure will drop, and that pressure drop will create a sufficient driving force between the float chamber and the middle of the fuel discharge tube, so that the driving force will allow fuel to come from float chamber to the intake duct. And for that we need to design in such a way that that drop in velocity, the increase in velocity, rather drop in pressure will be good enough to create a pressure difference, so that the required amount will be supplied from float chamber to the intake duct due to that pressure difference. And that we need to design that what will be the, it is basically orifice meter, that is we are having a constricted space, a restricted area, so that we can create we can drop pressure by increasing velocity, so that we have pressure difference. Fine. So, that means, but here when you are designing, you need to ensure that the the tip of the jet should be always higher than the fuel level of fuel in the float chamber. Otherwise, there will be a continuous supply of fuel from float chamber to the intake duct. That should not be there. So, the tip of the jet should be always above the fuel level in the float chamber. Otherwise, there will be a continuous supply of fuel from the float chamber to the intake duct. Therefore, so what we can see from this arrangement, that fine, the pressure difference between the cylinder and the ambience will allow, that is essentially created by the motion of the travel of piston from TDC to BDC, that will allow incoming air to come into the cylinder through air intake through the intake duct. While you are having flow of air through intake duct, we can provide projected areas, so that we can again create a pressure difference by increasing the flow velocity of air, so that pressure difference will create a driving force which will allow fuel to supply from float chamber to the intake duct through fuel discharge tube. So, with this I can supply air fuel mixture by properly designing the safe, rather passage of this restricted area, that is by properly designing the projected areas. So, this is the operational principle of a simple float type carburetor, and by how we can supply desired amount of air fuel mixture to the engine. But this is very important to mention here, that while you are designing this, so maybe using this simple float type carburetor, you can always provide constant amount of mass flow of air, mass flow of fuel, because it is not possible to change the restricted area that is there in the intake duct. So, while you are supplying using a simple float type carburetor, then of course we can provide always, depending upon the composition of the fuel, we can supply always what will be the required rather we can supply a constant amount of mass flow air and constant amount of fuel, that is a fuel air mixture or air fuel mixture that will be supplied will be constant. We cannot supply varying air fuel mixture or fuel air mixture depending upon the load requirement. That is why nowadays simple float type carburetor is now obsolete. Anyway, only to have an understanding by how we can supply air fuel mixture through carburetor, we are doing this analysis. So now I said we should discuss about while we are doing this, while we are using the simple flow type carburetor, how we can supply, what will be the mass flow rate of air and what will be the mass flow rate of fuel, and for that we will do a little bit mathematical analysis. So if we go to the next step, that so here we can see that initially we are having a pressure difference between section AA and inside the cylinder, for which we are having supply of mass flow rate of air, while we are having flow rate of air through the air intake, through the intake duct, then we are providing projected areas at the middle, and while we are doing so we are increasing velocity and we are dropping the pressure, and that drop in pressure will create pressure difference between float chamber and the middle of that intake duct, and that will allow fuel to flow from float chamber to the intake duct. Anyway, so now if we will analyze that how we can calculate mass flow rate of air and mass flow rate of fuel for this particular configuration. So if I assume that the process is steady state steady flow, so for a steady state steady flow process, for a steady state steady flow process, we will see how we can have a steady state steady flow process, because it is not always possible, because we are supplying air fuel mixture only. If it is a 4-stroke engine, then we are supplying air fuel mixture only during the intake stroke, and rest other strokes we are not supplying air fuel mixture. So how we can maintain a steady flow steady state process? But we will discuss that now what will be the assumptions, rather, by how we can have this analysis valid for this particular case. So for a steady state steady flow process, if I write again, if I process between section AA, between sections AA and sections BB, then what I can write, right? So what I can write, that HA plus CA square by 2 plus Q is equal to W plus HB plus CB square by 2. Q and W are the heat added and work transfer, and then HA and HB the enthalpy at point section A and BB, CA and CB the flow velocity of air at section A and section BB. Fine. Now in absence of heat and work transfer, so right, so this is the steady state steady flow process I can write. So now what we can write, in absence of work and heat transfer, this equation will be HA plus CA square by 2 is equal to HB plus CB square by 2. That means if I write this equation between sections A and BB and there is no heat and work transfer, then this equation will be this, HA plus CA square by 2 plus HB plus CB square by 2. Here we have to write again, at section A, condition is ambient. Rather, section A is a condition is ambient, right, and for above from intake section, and for above from intake section. Also the area of section A is much greater than section BB, so we can assume, we may assume CA almost equal to 0. So section A condition is at ambient, and for above from intake section, so we can assume CA is equal to 0. Rather, cross sectional area of A is much higher than cross sectional area of BB, so that this assumption is not a very bad assumption. So if that is the case, then I can write HA is equal to HB plus CB square by 2. Therefore, CB is equal to 2 HA minus HB of root, that is velocity of air at section BB is equal to HA minus HB twice of HA minus HB root of that. So if I assume for an ideal gas assumptions, because we have to assume they are only air, so for an ideal gas assumption, this HA I can write Cp into TA. Therefore, an HB is equal to Cp into TB Therefore, I can write Cb is equal to root of twice into Cp into Ta minus Tb. So, that is the rather I can write twice Cp Ta into 1 minus Tb by Ta under root of that. So, now that is what we have so Cb, the velocity of air at section Bb is like this. So, if I know the because I know temperature at air at section A because it is ambient condition, but we have to calculate temperature at point B. Now, if I attach a U tube manometer at section Bb, then one side it is ambient, other side is connected to the middle of the section that section Bb, then we can calculate pressure. So, we can calculate pressure at section Bb by only attaching our U tube manometer because one side of it is the atmospheric pressure. Fine. So, we have calculated Cb. Now, if the process between Cb and A to be isentropic process, again we are assuming the process between A and Bb have to be isentropic process because there is no heat transfer, and if we assume that the frictional loss is very less, so we can assume the process between section AA and BB is isentropic. So, process between section A and BB is isentropic. This is not again a very bad assumption because there is no heat interaction between the between these two sections, and also the frictional loss is very negligible, you can assume, because viscosity of air is very less. Anyway, in a true sense it is not isentropic process, but we can assume the process is isentropic. If that is the case, because if we look back, if we go back to our previous slide where we have seen that I can calculate Cb, or you can directly get pressure by attaching a U tube manometer, but here Tb is unknown because we know Ta, we know Cp. So, if I write if I assume the process is isentropic, then what can I write? Tb by Ta, that is ideal isentropic process, that will be Pb by Pa to the power gamma minus 1 upon gamma, right. Therefore, Cb that will be equal to root of twice Cp into Ta into 1 minus Pb by Pa to the power gamma minus 1 upon gamma to the power half. So, what will be mass flow rate of air? That is very important. Mass flow rate of air, because we have to calculate mass flow rate of air at that section, that is the venturi, where we have provided projected areas. So, mass flow rate of air at section Bb, because mass flow rate of air at section Bb, that is very important. Because of that mass flow rate, we will get what is the amount of mass flow rate of fuel. So, because of that, this amount of mass flow rate, what we will obtain the mass flow rate of fuel at that section. So, we need to calculate mass flow rate of air only that section where we are providing venturi, other projected part, because of the pressure difference, because of the drop in pressure over there, we will have a continuous supply of fuel from float chamber to there. So, mass flow rate of air at section Bb, that is m dot ABB, mass flow rate of air m dot ABB, that will be equal to rho b area of section B into Cb. So, rho b into area of section B into root Cp Ta into 1 minus Pb by Pa to the power gamma minus 1 upon gamma to the power half. Now, Pb information I can obtain from the U tube manometer that I have attached with that section Bb. Fine. So, this is the mass flow rate of air at section Bb. Now, we have assumed isentropic process. So, again for an isentropic process I can write, for an isentropic process what I can write, T is proportional to P power to the power gamma minus 1 upon gamma, that I can obtain from the above expression. If that is the case, that means T is proportional to rho RT to the power gamma upon 1 minus gamma. Therefore, if I do this analysis, I can write T to the power 1 by gamma will be proportional to rho to the power gamma minus 1 upon gamma. Therefore, T is proportional to rho to the power gamma minus 1. This is very important for an isentropic process. Therefore, I can write that Tb by Ta to the is equal to rho b by rho a to the power gamma minus 1, or therefore, rho b is equal to rho a into Tb by Ta to the power 1 upon to power 1 by gamma minus 1. This is very important because if I look at the expression of mass flow rate of air at section Bb, their unknown is rho b. because we know area we can calculate. So, unknown is rho b. So, I have now expressed rho b in terms of rho a and T b by T a. So, that is again I can write rho a into T b by T a is equal to, so P b by P a to the power 1 upon gamma, because T b by T is equal to P b by P to the power gamma minus 1 upon gamma. So, it will be 1 by gamma. So, now we have expressed rho b in terms of P b by P a. So, if I plug in this expression in the mass flow rate of air in at section B b, so we will get again m dot air at section B b, that will be equal to rho a into P b by P a to the power 1 by gamma a b root of twice C p T a into 1 minus P b by P a to the power gamma minus 1 upon gamma to power half. So, if I now put this value of P b by P a inside the square root, then I can write this will be rho a b root 2 C p T a into P b by P a to the power twice by gamma minus P b by P a to the power gamma plus 1 upon gamma to the power half. So, this is the expression of mass flow rate of fuel at section B b. So, this is the expression of mass flow rate of fuel at section B b, that is what I obtain. So, this is mass flow rate of fuel at section B b, P b by P a to the power 2 by gamma. So, I have expressed mass flow rate of fuel at section B b in terms of known quantities, because I know rho a, I know area B, and P b by P a, that information I can obtain by attaching a new tube manometer at section B b, because whose one side is open to atmosphere. So, this mass flow rate of air whatever we have obtained is not actual mass flow rate, rather this is ideal mass flow rate, because we did not take into account the frictional losses, and that is why we have used isentropic relationship. So, this is ideal mass flow rate, ideal mass flow rate. So, this is the expression of ideal mass flow rate. Now, to get actual mass flow rate, what we have to do? So, mass flow rate of air at section B b actual will be mass flow rate of air at section B b into a factor, that factor is known as discharge coefficient. So, C d A. So, this is known as discharge coefficient, whose value is very small, 0.9 like this. So, we have to multiply a discharge coefficient just like a flow through orifice meter or venturi meter. That means, we have calculated mass flow rate at section B b using following an isentropic process. There we did not consider the frictional losses, but in reality there will be frictional losses, and to take into account that losses, the actual mass flow rate will be always less than that predicted by this equation, and that will be multiplied by a factor which is known as coefficient of discharge or discharge coefficient. So, now very important, CDA is value is almost equal to 0.9. So, value is almost equal to 0.9. Now, while we have calculated mass flow rate of air at section B b, we have assumed the flow to be steady state steady flow process, but as I said that we are supplying air fuel mixture only during intake stroke, while if it is a 4-stroke engine, 3 other remaining strokes are ideal. So, they are during that stroke we are not supplying air fuel mixture, other intake valve is remaining open. Then how we can assume that the process to be steady state steady flow process. So, to what extent the steady flow process is valid, that is very important. So, to what extent the steady state steady flow process is valid. As I said you, if it is a 4-stroke engine, only we are supplying air fuel mixture during intake stroke, for the 3 remaining other strokes we are not supplying, rather intake valve is remaining closed, then how we can assume steady state steady flow process. So, this assumption is more valid, for multi-cylinder engine, and 2-stroke engine, because if it is a multi-stroke engine, maybe when intake is 1 stroke, maybe idle in other cylinders. So, here we are having continuous intake stroke in either in in any one of the cylinders in a multi-cylinder engine. So, if it is a multi-cylinder engine, we have to supply air fuel mixture always. So, it is valid for multi-cylinder engine and also for two-stroke engine. If it is two-stroke engine, maybe only one stroke is intake, other stroke is exhaust. So, that is also valid, but in a four-stroke engine it is not valid at all. Four-stroke single-cylinder engine, no intake, so not accept. So, four-stroke and single-cylinder engine, this steady state steady flow process is not valid, not steady state steady flow process is valid. So, it is valid only for that is valid only for multi-cylinder and two-stroke engine, fine. So, we have calculated mass flow rate of air at section B. Now, we have to calculate mass flow rate. What will be the mass flow rate of fuel at section BB? Because that is, if I calculate mass flow rate of fuel at section BB, then we can calculate fuel air ratio or air fuel ratio, that is fine. So, if I would like to calculate mass flow rate of fuel at section BB, so again if I assume that this is a section CC, so maybe if I assume that this is the section CC, so maybe this is section CC. So, again we have to write steady state steady flow process in for a flow. So, if I now again write steady flow energy equation or steady flow energy equation between section CC and to obtain mass flow rate of fuel at section BB, we have to apply steady flow energy equation between section BB and section CC. So, we are applying steady flow energy equation between section CC and BB. So, this is very important. We have to apply steady flow energy equation between sections CC and BB and that is required to obtain the mass flow rate of fuel. So, if I apply mass flow now for the flow of fuel, if I apply this equation between, so for a flow of fuel, for the flow of fuel, if I apply that equation between section CC and BB, if I go back to my schematic where we have drawn that simple float type carburetor, so then delta H is the difference between the fuel level in the float chamber and the section BB. But now a question may arise that the float in a float chamber we are having a float, simple float. So, this float will allow a continuous, it will allow to maintain the level of fuel constant in that float chamber. So, whenever there will be a drop of the level and drop in level of the fuel in the float chamber, float will allow fuel to come into the float chamber from fuel tank. So, the purpose of providing a float valve or the float is to provide a constant level of the fuel in the float chamber. So, if we can maintain a constant level of fuel in the float chamber, that means it will always will be in the section CC. So, now if I write this equation between section CC and section BB, then for the flow of fluid what I can write, mind it, at section CC again condition is ambient. So, section CC, at section CC, so at section CC condition is, section CC is at ambient, right. So, atmospheric pressure and atmospheric temperature, that is there. So, if that is the case, then how if I write that for the energy equation for the flow of fluid, I can write that PA, that is pressure at section CC, that by rho fuel plus PC, rather PC plus C square by 2 is equal to PB by rho F, because now we have to take density of the fuel itself because it is not air, rho F plus CB square by 2 plus delta P friction, because whenever fuel is divided by rho F plus G into delta H. So, whenever fuel is flowing from float chamber through discharge tube to the air intake duct at section BB, of course we have to take into account the frictional losses, and that is why we are writing anyway. So, delta P friction is the frictional losses due to friction and surface tension. So, this is the friction and due to surface tension, etc., right. So, again we have to take assumptions. What is the assumptions we are going to take? What are the assumptions? Assumptions, one is Cc is much less than Cv, that the velocity of fuel at section Cc is much less than at section Bb. That is justified because area at section Cc is much higher than at section Bb, so that Cc square by 2 can be neglected. Again this assumption is not a bad assumption, because cross sectional area at Cc is much greater than cross sectional area at section Bb. So, this assumption is not a bad assumption. So, this can be neglected, and also we are taking that ideal fluid flow. So, rather delta P Fr almost equal to 0, that is frictional loss is neglected. Losses due to friction and surface tension is neglected, fine. So, if I write this, then equation becomes Cb square by 2 will be equal to Pc minus Pb divided by rho f minus g into delta H. Therefore, Cb will be equal to twice into Pc minus Pb divided by rho f minus twice g into delta H of under root. So, this is the velocity at section Bb of fuel. So, this is the velocity of fuel. So, there this is Cb, here Cb and Cc are the velocity of fuel at sections Bb and Cc respectively. So, the velocity of fuel we have obtained at section Bb is equal to this 2 of Pc minus Pb by rho f minus 2 g into delta H. Delta is the difference in height between the float chamber and the section Bb. What is fuel level in the float chamber and the section Bb. So, if I write it, so we have obtained the velocity of fuel. So, then how I can obtain the mass flow rate of fuel at section Bb? Therefore, we have obtained the velocity of fuel at section Bb, that is Cb is equal to twice into Pc minus Pb divided by rho f minus twice into z into delta H under root. Note that Pc is almost equal to atmospheric pressure, P atm. Therefore, I can write Cb is equal to twice P atmospheric minus twice Pb divided by rho f minus twice g into delta H, that is the velocity of. So, this is the fuel velocity at section Bb. So, what will be the mass flow rate of fuel at section Bb? So, mass flow rate of fuel at section Bb, that is m dot fuel at section Bb will be equal to rho f area B into Cb, that is expression. So, that means rho f AF rho f twice Pa minus Pb divided by rho f minus twice g into delta H. Here delta H, that information is known, Pa atmospheric pressure I know, and Pb that can be obtained by the U-tube manometer. So, that is the pressure at that section Bb. Area at section Bb, that I know, area at section B, and density of fuel I know. So, I can write this AB into twice rho f Pa minus Pb minus twice that is twice G into H, twice into G into H, twice into G into H. So, twice into G into delta H into rho f. So, if I take this and that I will get expression like this. So, right, rho f into G into H. So, if I this is the explosion rate of mass flow rate, a mass flow rate of fuel at section BB. So, this is the explosion rate of fuel at section BB, and rather instead of writing this I can write this is the expression. So, mass flow rate of fuel, that is mass flow rate of fuel at section BB, and this will be the again ideal mass flow rate because we did not take into account the frictional losses. So, that is AB into rho f root of twice Pa minus Pb divided by rho f minus G into delta H twice. So, this is the expression of mass flow rate and this is again ideal. So, we have to obtain mass flow rate of fuel at section BB. Actual will be again mass flow rate of fuel at section BB ideal into coefficient of discharge coefficient, fuel discharge coefficient CDF. So, this is the mass flow rate, actual mass flow rate that I can obtain by knowing the CD. So, we have obtained by doing a simple analysis and using a simple float type carburetor what will be the mass flow rate of air and mass flow rate of fuel at section BB, because our aim was to calculate mass flow rate of air and mass flow rate of fuel at section BB, and for that we have calculated taking a few assumptions, and those assumptions are not very bad assumptions because we have explained all those. But the mass flow rate of air and mass flow rate of fuel that you obtain, those are the ideal mass flow rate. In actual case the flow rate will be lesser than that predicted by those equation because we did not take the frictional losses into account. Now, question is, so if you use a simple float type carburetor, we have discussed that okay fine, we are using a steady state steady flow process, we are taking an assumption, but that assumption is valid only for multi cylinder and 2 stroke engine, but for a single cylinder and 4 stroke engine this assumption is not valid at all. And the area provided at section BB, because of that projected parts there will be a drop in pressure because of the increment of velocity, and that pressure difference will create not only because that pressure difference will create a continuous supply of fuel from float chamber to that section BB, and because of what we are calculating mass flow rate of fuel and air at that section only. So, now question is, when we know the mass flow rate of air and mass flow rate of fuel at section BB, then from there we can calculate what will be the fuel air ratio or air fuel ratio. And as I said you, if I use a simple float type carburetor, when we are designing that particular projected parts, we can't change depending upon the requirement of load, and if we cannot change the projected parts or projected area, we cannot change the mass flow rate of air and mass flow rate of fuel, and that is why simple float type carburetor is not used nowadays. But this is the concept by how we can have a flow of fuel without having external pump using a simple float type carburetor. Nowadays what is done, because air will come through intake manifold because of the because of the pressure difference that was created by the movement of the piston itself, because when piston is coming from TDC to BDC, that movement of the piston itself creating a vacuum pressure inside the piston cylinder, which in a sense create a pressure difference between the ambience and the inside between the ambience and engine cylinder, and that pressure difference allow air to be introduced in the engine cylinder during intake stroke. But in case of a supply of fuel, we need to use a fuel pump, and that is what is done in case of in most of the modern CI engine, because we are having fuel pump, and fuel pump supplies fuel through injected into the cylinder. But even for SI engine, since we have discussed that simple float type carburetor don't serve the purpose to supply varying air fuel ratio or air fuel mixture or vice versa, depending upon the requirement of load that we have discussed, that in idling condition, in cruising zone, idling zone and power zone, we may require different ratio of different fuel air ratio or air fuel ratio. If that is the case, it is really impossible to supply that using a simple float type, it is not possible at all using a simple float type carburetor, and that is why the simple float type carburetor is replaced by a modern carburetor, where we have to supply fuel through fuel, or we can supply only air through air intake manifold, and we can supply fuel through fuel pump. And the requirement of air fuel mixture and fuel air mixture that you have discussed, that varies from in 3 different zone. When we are starting engine, maybe with that time only to keep the engine in startup mode, we need to supply air fuel ratio, and that air fuel ratio, that fuel air ratio will be higher than what is required during cruising zone. In most of the time, engine should run in a cruising zone, and there we require a constant flow rate, constant value of fuel air ratio. But while during idling zone, engine is supplying no load, but still it is running, still it is in startup mode. So we have to supply higher fuel air ratio, and we will discuss why it is happening so. And also in the power zone, when engine is providing, because we need higher power from the engine, that time we have to provide higher fuel air ratio, that is quite obvious. But during idling zone, even without having no load from the engine, we need to supply higher fuel air ratio, that we will discuss in systematically. So from here we can say that the discharge coefficient of air that you have seen, that 94.99, but the discharge coefficient CDF represents the effect of here. While you are calculating actual mass flow rate of fuel, we have multiplied the ideal expression with the coefficient constant, which is not discharge coefficient of fuel. So this is discharge coefficient of fuel CDF, and this because it takes care of all the deviation that we didn't consider during the analysis, right? But it influenced by many factors, which is but this discharge coefficient which ideal deviation from 1D isentropic flow, because we have considered one dimensional isentropic flow while you are considering while you are trying to calculate the mass flow rate of air and mass flow rate of fuel. So it is, so the actual mass flow rate of fuel will be to obtain the actual mass flow rate of fuel, we have to multiply the ideal expression using a coefficient, discharge coefficient CDF. But the most important this discharge coefficient CDF is influenced by a few factors, and most important factors are that fluid specific gravity. So I am writing that CDF, that is discharge coefficient for fuel, which is which this factor needs to be multiplied with the ideal expression only to obtain actual mass flow rate of fuel. But there are several factors which influences this, several factors which influence this discharge coefficient of fuel. The most important are, number 1 is fuel specific gravity, rather fuel is fluid, of course it depends upon fluid specific gravity. Fuel is of course fluid specific gravity. Number 2, fluid viscosity. Number 3, fluid surface tension. So these 3 are the most important parameters that influence the coefficient of discharge, or the discharge coefficient of fuel, and for that we need to multiply because we didn't consider all these factors while we have calculated the mass flow rate of fuel at section BB. So that means using a simple float type, what is the conclusion for today's analysis is that using a simple float type carburetor, how we can provide the mass flow rate of air, and without providing a fuel pump, rather providing a fuel pump, by changing the design of the air intake duct, how we can supply fuel from float chamber to that duct. That is what we have discussed, and also we have discussed how we can calculate the mass flow rate of fuel and mass flow rate of air at section BB. Of course, for that we have taken a few assumptions, and those assumptions are not very bad assumptions, because and finally, although we have carried out one dimensional isentropic analysis, but we didn't consider a few, because there will be a deviation from if we have used one dimensional isentropic analysis, but and that is why the mass flow rate of air and mass flow rate of fuel, whatever we have calculated, all those are ideal, but to obtain the actual values we have seen that ideal expression will be multiplied by discharge coefficient, and then we can obtain the actual mass flow rate of fuel and actual mass flow rate of air. From there we can calculate what will be the fuel air ratio being supplied by that particular carburetor to the engine. And we have discussed that the simple flow type carburetor is not able to supply varying fuel air ratio depending upon the load, that is why nowadays it is not used. And finally, we have discussed that discharge coefficient of fuel which we did not take into account, it varies, it influenced by several factors, and we have identified a few factors like fluid specific gravity, fluid viscosity and fluid surface tension. So, we will discuss that if we need to vary mass flow rate of air and fuel for different engine requirement, that is what we have discussed, that idling zone, cruising zone, power zone. We will discuss in detail that aspect in the next class, and with this I stop my discussion today. Thank you very much.